Hello, historical geology students. Here's another video for you to watch. We finished talking about minerals and sedimentary and igneous rocks. Now we want to talk a little bit about sedimentary rocks. Sedimentary rocks are formed on the surface of the earth under low pressure and temperature conditions. In your lab, you tried to figure out the depositional environments where these sedimentary rocks formed. That's where the sediments are deposited. Sedimentary rocks are laid down in layers, which we call beds or sedimentary beds. So sediment is basically gravel, sand, silt, or clay. And it's deposited by water, wind, or ice. So water, wind, or ice moves the sediment, and then it deposits that sediment somewhere else. And that somewhere else is called the depositional environment. So first thing that we need to talk a little bit about we talked about there being three kinds of sedimentary textures: detrital, biochemical, which is also called biological or organic, or chemical. What's the difference between these three kinds of textures? Well, the first texture is detrital, and that means that that rock is made of gravel, sand, silt, or clay. And the second type of sedimentary rock is a biological or organic or biochemical sedimentary rock, and that involves some sort of living organisms. Some creatures died in order to make that rock. Something that was living died to make that rock. Third sedimentary texture is a chemical sedimentary texture, and that means that water evaporated, and water contains chemicals in it, and those chemicals will crystallize out in minerals and form chemical sedimentary rocks. When we're talking about detrital sedimentary rocks, we figure out the rock name we figure out a detrital sedimentary rock name based on the size of the sediment. And we can divide sediment into four main classes or size categories. The first is called gravel. Gravel is more than 2 millimeters in diameter. 2 millimeters, a millimeter is about the thickness of a dime. So a gravel can be pea-sized or even walnut-sized. It's big. Think of the gravel on the bottom of an aquarium. That's what or the river gravel, the rounded pebbles you see on the bottom of a stream bed. That's gravel. Smaller than gravel is sand. Now, you all know what sand looks like intuitively. You've seen sand growing up in a stream bed, or you've seen sand on the beach, or in the sandbox that you played in when you were a kid. But scientists always have to put numbers to everything, and we have these numbers for sand. And sand is a particle between 1/16 of a millimeter to 2 millimeters in size, in diameter. So sand is found in rocks like sandstone, quartz sandstone, or arkose are made of sand. And you can see the individual sand grains in a quartz sandstone or in an arkose. Gravel makes breccia and conglomerate. If it's got rounded pebbles in it, it's called conglomerate. If it's got angular pebbles in it, it's called breccia. Smaller than sand, we have silt, which has a diameter 1/256 of a millimeter to 1/16 of a millimeter. It's almost powdery. If you hold silt between your fingers, it feels like grit. The particles are smaller than sand. The old timers used to figure out what a siltstone is. A siltstone is a detrital sedimentary rock that's smaller than sand, And by rubbing the siltstone against their two front teeth, and you could feel that gritty. It feels gritty. You don't want to do that too much because it'll lead to tooth decay, though. But the next rock, the finest grain of all of your detrital sedimentary rocks, is made of clay. And these are tiny particles, less than 1/256th of a millimeter in diameter. These particles are so small you can't use a regular microscope to see them. You need to use something called an electron microscope to see them. And when they get deposited, they make shale. Bottom line is the following rocks are detrital. Conglomerate and breccia, which are made of gravel. Quartz sandstone and arkose, which means they're made of sand. Siltstone comes in many different colors, so you got to identify these on size, not color. Is made of silt, and clay makes shale. Those are your detrital sedimentary rocks. So here, this is what a quartz sandstone looks like under a microscope, and you can see the Q's here represent quartz, and the yellows are calcite. So the quartz grains here are cemented together by this calcite cement, and that occurs underground as the sand is deposited, and the ground and more layers are deposited on top of those sand beds, so that sand bed is deep underground under the water table, and then calcite will crystallize out and cement these sand grains together to make a quartz sandstone. So to change gravel, sand, silt, or clay into a detrital sedimentary rock, two processes can be involved, either compaction or cementation. Compaction means that you got a sedimentary bed deposited, another one deposited on top of it. So finally, this bed is down here, and it's being pushed on by the overlying sedimentary beds, and that compresses silt into siltstone or clay into shale. Another way that you can make a detrital sedimentary rock is through cementation. So let's say you have sand grains or gravel, and they're deposited, and then eventually other layers are deposited on top of it. These layers end up being below the water table, and then quartz or calcite cement can cement together sand grains to make either quartz sandstone or arkose, or it could cement together round pebbles to make conglomerate, or it could cement together angular pebbles to make breccia. Here's a typical detrital sedimentary rock. What type of detrital sedimentary rock is this? Think about it. You're smart people here, and you can figure this out. First of all, it's made of chunks of rock, and therefore it must be detrital, right? It's not biological, it's not chemical. Biological, there'd be evidence of life in it. Chemical, it'd be made of little crystals. So it's got rounded pebbles in it. So what do you think this rock is? You're right. I hope you got it right. And it's conglomerate. Rounded pebbles. Where do you find rounded pebbles in nature? Think about it. You find them on the bottom of riverbeds. So a possible depositional environment for conglomerate would be a river. But you also find round pebbles at the seashore as pebbles get move and roll on the bottom of the seafloor, and then back and forth with the waves and the tides. The pebbles get rounded. So another possible environment for a conglomerate is shallow marine. To figure out whether or not this particular conglomerate bed formed in a river or in the shallow ocean, what would you do? Well, one thing you could do is there might be some evidence, a small amount of evidence, like seashells in there that might tell you that this formed in the shallow ocean, or maybe freshwater plants or bones of freshwater fish in here, and therefore it could have formed in a river. Still, this is a detrital sedimentary rock, even if you do find those things in it, because any rock made of gravel, sand, silt, or clay is a detrital sedimentary rock. Limestone. Most of y'all got this right in lab, but on the quiz you're going to have to figure it out yourself. And limestone comes in so many different colors. It comes in light gray, medium gray, dark gray, brown. So you can't identify a limestone just based on its color. But one thing that you can use when you get your rocks for the lab quiz is limestones will always react to acid. Why? Because they contain the mineral calcite. And so if a rock has calcite in it, it will react strongly to acid. There are two special types of limestone, though, that you need to know about, chalk and coquina, that are a little bit different than regular limestone. Chalk, you can write with it. Coquina is made of actual seashells, like this one here. If you have fossil seashells, not actual seashells, it's just a plain old limestone. But if it's got actual real shell bits in it, like this, it's a coquina. All limestones will react with acid. If you want to learn more about sedimentary rocks, you could take physical geology this summer. Next type of rock we want to talk about is called a metamorphic rock. As I mentioned before, a metamorphic rock is a rock that has changed due to increased pressure in the earth. In other words, being buried by other rocks, for example. There'd be pressure put on those rocks, or increased temperature, or hot fluids flowing through those rocks. So a metamorphic rock was something else in the past, and it's changed to the metamorphic rock that we now see today. Where do you think that change is going to occur? At the surface of the earth or beneath the earth? Think about it. As you go deeper in the earth, temperatures get higher, pressures get higher. So you're more likely to form metamorphic rocks deep underneath the earth. Sedimentary rocks are formed at the surface of the earth. Igneous rocks are formed originally deep under the earth where temperatures are high enough to melt rocks, to make magma. If the magma reaches the surface, it becomes lava. If the magma cools underground, it forms a plutonic igneous rock with a phaneritic igneous texture. If the magma reaches the surface of the earth and erupts as a volcano, the lava will flow down the sides of the volcano to make volcanic rocks, which will have an aphanitic texture, small crystals in it. Metamorphic rocks can be divided into two main types. So, for igneous rocks, you need to know about the aphanitic and phaneritic textures and the vesicular textures. And for the sedimentary rocks, you needed to learn about detrital, chemical, or biological textures. For metamorphic rocks, it's a lot simpler. There's two textures. You got foliated metamorphic rocks, and you got nonfoliated metamorphic rocks. What does a foliated metamorphic rock look like? Well, here you can see a common foliated metamorphic rock, and it's taken under a microscope, and it's got this layering to it. And this layering is this foliation, this layering in the rocks, which is called foliation, is formed by increased pressure. So, pressure is always involved in making foliated metamorphic rocks. Here you can see a whole bunch of crystals in a rock. Maybe it's an igneous rock. Then you put that rock under higher pressure, and the minerals all line up. And that the lining up of these minerals reveals itself to you visually by showing a layered structure. So this rock perhaps was squeezed by higher pressures. Regardless, whenever you see a foliated metamorphic rock, you know one thing for sure, that pressure was involved. Let's take a look at some different metamorphic rocks. And we'll type in foliated metamorphic rocks so you can take a look at them. This is a nice picture that might help you understand how metamorphic rock forms. Here you can see a sedimentary rock called shale. It's not metamorphic. It's a detrital rock. Depositional environment, a lake made of clay. If you increase pressure in the earth, you will make a foliated metamorphic rock called slate. See the layering or the foliation in this metamorphic rock? You can see the layering in the slate. If you increase pressures even more, and maybe temperature too, but always pressure, you will make another type of foliated metamorphic rock called phyllite. Now you can see that the layers are curvy and the rock looks a lot different from its original parent. This is what we call the parent rock before it got metamorphosed. It looks much more different than the parent. It's called phyllite. If we increase pressures and temperatures even more, like deeper in the earth, we can make another type of metamorphic rock called schist, schist. And notice that the crystals have grown even larger, and there's a more pronounced foliation with schist. If we increase pressures and temperatures even more, we can make a gneiss. Some people call it gneiss or gneiss, depending on what part of the country you're from, where the minerals have aligned themselves into layers of different colors. Some people call this type of foliation like a layer cake sort of look foliation. Regardless, you can see layering in all of these metamorphic rocks, and that's called foliation, formed by pressure. Since gneiss requires the highest pressures and temperatures to form, we call it a high-grade metamorphic rock, whereas schist or phyllite be more of a medium grade, and slate hasn't changed too much from its parent, so it's called a low-grade metamorphic rock. So metamorphic rocks are graded. In other words, we try and figure out how much did they change? Just a little bit, as in slate, or a lot, like gneiss. Non-foliated metamorphic rocks. Before we get into non-foliated metamorphic rocks, let's take one more look at the foliated one so we get this under our belt. This is slate. If you live in Oak Ridge, you might have slate tiles in your house. It's sold in 12 by 12 or 16 by 16 or 24 by 24 inch squares, and you can lay it down in your house, and it gives a beautiful look to it. It's a beautiful floor tile. Slate. It's a metamorphic rock. It's foliated. Phyllite, and this is a gneiss. This is another rock that is called migmatite. It's also foliated. It's got curvy layers in it. It's a very high grade metamorphic rock. It's the highest metamorphic grade rock there is. Non-foliated metamorphic rocks. Since this is historical geology, we're just covering the basics of metamorphic rocks. But if you're interested in this summer we'll be teaching a lot about metamorphic rocks and physical geology. So if you really like rocks and minerals, physical geology is going to be your cup of tea, and we'll have a class this summer. But the two non-foliated metamorphic rocks we're going to look at are marble and quartzite. Who are the parents of marble and quartzite? Well, limestone is the parent of marble. You probably know by now that limestone has calcite in it, right? And if you take a limestone and expose it to higher pressures and temperatures, it's going to change into marble. The metamorphic rock marble, its parent is limestone. Who's the parent of quartzite? Made of quartz, as you can tell by the name. It's Quartz Sandstone. Let's take a look at these more carefully. we're going to take a look at non-foliated metamorphic rocks. These are metamorphic rocks that do not have foliation. So here you got a foliated metamorphic rock and a non-foliated metamorphic rock. First one we're going to look at is quartzite. And quartzite could be pink, it could be green, it could be all kinds of different colors. Brown. So how do you identify it? Well, it's made of quartz, the mineral quartz, which will scratch glass. And it's a beautiful rock that's used to make flooring tiles and countertops. And the crystals grow interlocked together. And that's how we could tell quartzite. Here's what quartz that kind of has a sugary look to it. That's something that might help you. If you're not sure if that's a quartzite, take a piece of glass out and see if it'll scratch glass. If it's got a sugary look to it like this, that's a non-foliated metamorphic rock called quartzite. The other non-foliated metamorphic rock that you need to know about is marble. And you know, if you might have marble floor tile in your bathroom, and you can buy it at Home Depot or Lowe's in 12 by 12, 16 by 16, or 24 by 24 inch tiles, and you can lay that in your bathroom. It's beautiful. The crystals grow together just like in quartzite, and they come in different colors. Marble comes in pink, like in the White House. The White House marble's pink, or it could be white or gray. It could be green, but it's always made of the mineral calcite. What do you think is going to happen if you drop acid on marble? It's going to react strongly, because any rock that has the mineral calcite in it will react strongly to acid. It doesn't look anything like its parent, limestone, sedimentary rock limestone. It looks like beautiful crystals. In fact, the crystals are so beautiful that we make floor tile or statues, marble statues. The ancient Greeks and the Romans made beautiful statues out of marble. And here you can see one by Michelangelo. And this is one that Catholics are really they admire this statue. Here you can see Jesus after he's taken off the cross during the crucifixion, and Mother Mary holding her son in her arms, and the sadness in her eyes. All of that can be depicted because marble can be cut and to reveal the human form very well. Michelangelo did another statue, the statue of David. And if you go to Italy, you can see all these things. So the statue of David, here with the statue of David. So when you think of marble, think of a beautiful stone that can be carved to reveal the details of the human form, or animals, or plants, or the expressions on people's faces. Think of the great artists in Rome and Greece. Think of the beauty of this rock. Think of maybe he couldn't satisfy his wife. I'm sorry, I shouldn't have said that. Okay. Anyway, marble is a non-foliated metamorphic rock. You got to have some humor, otherwise it gets boring. Anyway, let's go over to the third chapter, plate tectonics. This is chapter number 3. This is going to be on the test. And plate tectonics. This chapter is very important, ladies and gentlemen. Really study this chapter, because plate tectonic theory is the most important theory ever introduced into the field of geology. Let me put it like this. Before the theory of plate tectonics, we knew we had mountains on the edges of continents. We didn't know why. We knew we had volcanoes along the edges of the Pacific Ocean, in the Ring of Fire, and along the Mediterranean. We didn't know why. We knew that the continents fit together like pieces of a jigsaw puzzle. We didn't know why. We knew we found oil and natural gas in the Gulf of Mexico, in Texas and Oklahoma. We didn't know why. Plate tectonic theory shows the beauty of science when one theory explains everything. This one theory explains almost everything on our planet, geologically speaking. Prior to plate tectonics, most people believed in permanism, which is they believed James Ussher's idea of catastrophism, which said that the Earth was 6,000 years old and it was formed and hasn't changed since. So that means North America and South America have always been at the same longitude and latitude. The width of the Atlantic Ocean has always been the same. The Appalachians and the Rockies have been here since the beginning of Earth history. We now know that's not true. The data overwhelmingly shows that the continents move. And now we know why we have earthquakes and volcanoes and mountains. It's all understandable if we understand the one theory called plate tectonics. In order to understand plate tectonics, we first need to know about the theory that led to plate tectonics, called continental drift. Continental drift is not plate tectonics. It would lead to plate tectonics, and it was introduced to the world by a German scientist by the name of Alfred Wegener. I don't know if you speak German or not. Sind Sie sprechen Sie Deutsch? Ich spreche ein bisschen Deutsch. I can speak some, but W is V, ein Deutsch in German. It's Alfred Wegener. In 1912, introduced the theory of continental drift to the world. Here is Herr Wegener in Greenland, and in the next video we'll start talking about continental drift.